a multiplexer to implement this function. There are different ways to implement this function, and some are easier than others, and it's not necessarily true that a multiplexer is the easiest way, but you're going to just like learn, how you can do it, and then in the future you can decide if it would be useful for your particular function. So the way I recommend doing it, there are different ways. I'm not saying this is the only way. This is the way that makes sense to me. So you might come up with a different way. So the first thing I'm going to do is I'm going to make a truth table that has X, Y, Z, and W, that has all 4 variables in it. And I'm also going to label the min terms. And I'm going to have a column for my function to say whether my function is 1 or 0 at that time. So (16), 2 to the 4th. So these are the numbers from 0 to 15. And when I was practicing this, I practiced with the function that y'all are actually doing. I didn't practice with this function, which I made up. So y'all do check me, and if it seems like I'm making a mistake, say, hey, is that supposed to be, a 1 or a 0? So we can double check it. Okay, so this function is the sum of the min terms 0, 1, 3, 7, 11, and 14. So that means in 0, 1, 3, 7, 11, and 14, I'll have a 1, and everywhere else I'll have a 0. Now, if we had, I'm going to pause for a minute until everybody has written stuff so that y'all can pay attention. I'm also going to pause the video. So please remind me when I start talking again to turn the video back on. Thank you, thank you. If we had a 16 to 1 multiplexer, this would be super easy. Because if we had a 16 to 1 multiplexer, which we don't have, then what we would do is we would have, we would do X, Y, Z, and W as our inputs. And then we would put a 1 into any of the ones that were the numbers that were in our min terms, which was, what was it, 1, 3, 5, 7, I don't remember what it was. Someone tell me? 11 and 14. Okay. And then we would put zeros into all the others, because our inputs would just be our values. That would be our truth table. It would just be exactly our truth table. But we don't have a 16-to-1 multiplexer, and while we could make one with two 8-to-1 multiplexers, I don't think that's what the intent is. So instead, we're going to choose 3 of these to be our control, and then the other one is just going to be part of a circuit. So we can choose either X, Y, and Z, or Y, Z, and W. I mean, we could also choose X, Z, and W, but that's a little harder just because of how it's laid out. And so it doesn't matter to me much whether we choose X, Y, and Z or Y, Z, and W. And I think I'm going to choose X, Y, and Z to be our controls. So notice what happens. So I'm going to say X, Y, and Z are our controls. And if you look, X, Y, and Z are the same every pair here. And if we look at what those numbers are for X, Y, and Z, for X, Y, and Z, what binary number that makes up is 0, 1, 2, 3, 4, 5, 6, 7. So just the digits, just the bits X, Y, and Z make the numbers 0, 1, 2, 3, 4, 5, 6, 7. So now let's look at what F is in terms of W, because F will either equal 1, 0, W, or not W. F can only have 2 values, 1 or 0. And it's either 1 or 0, like for both of them. Well, you'll see as we go through. So let's look at when XYZ is 0. When XYZ is 0, what is F? It's 1. When XYZ is 1, F is the same as W. When XYZ is 2, what is F? So just look at the F column. It's 0. Did y'all see how it's W when F is 1? I mean when XYZ is 1? Because if I look at the W column, W is 0, 1. If I look at the F column, F is 0, 1. So F takes on the same value as W. So F is going to be just one of these 4 things. It's either going to be 1 for both values of W, 0 for both values of W, or it'll equal W, or it'll equal the complement of W. So what does it equal for when XYZ is 3? W. What about when XYZ is 4? 0. When XYZ is 5? W. When XYZ is 6? And when XYZ is 7? W, right. And so then the way you would set up your multiplexer is you would have X going to S0, Y going to S, X going to S1, Y, S going to S2, let me just start this over. X going to S2, Y going to S1, and Z going to S0. And then my inputs 0, 1, 2, 3, 4, 5, 6, 7. 0 is 1. So I'll have a 1. That's just high voltage. So 0 is 1. 1 is W. 2 is 0. And that's just ground. 3 is also W. 4 is 0. 5 is W. 6 is 0. And 7 is W not. So you would need a NOT gate. And that's how you would implement this function using a multiplexer. Do y'all feel like you got it, or you feel like you need to try another one to really understand it? Yes.
I'm sorry because I missed the first 2 minutes. But,
You didn't miss much. I said, while you were out, I said if we had a 16-to-1 multiplexer, let me explain what I said when you were out. If we had a 16-to-1 multiplexer, it'd be really easy, because we would take our truth table and we would just put in ones for all the ones where our truth table is 1 and zeros for where it was 0. And then when you came back in, I was starting on this, and what I did is I said we only have an 8-to-1 multiplexer, and so I can only use 3 of these as my control. And so I chose to use XYZ, and I broke it up to where my XYZ was the same by pairs. Okay, but then now go ahead.
But yeah. So we took 16 inputs and collapsed them into 8 so that we could use a 8-to-1.
Right. That's exactly what we did. And in order to do that, we couldn't just use ones and zeros over here because we have that fourth variable. And so that's going to show up over here in our inputs as well.
Right. Yeah, makes sense.
Okay, anybody else?
I just have a question about the drawing. So with the W, is there like, out of that node, is there 3 of them coming out? Like 3 wires coming out of that?
Yeah, so like your chip, what would be going into all of those things that I was calling out,
Yeah.
so, okay, so like, can anyone remind me what pins were what? Like what was pin 0? Somebody has it written down? No? Nobody has it written down? It's 1? And pin 2? I'm sorry, pin 1?
And one is W.
No, I'm sorry. I meant on this.
Oh, I don't have that down.
4, 3, 2.
I got it.
Okay, so pin 1 was 3. Pin 1 was 3. So pin 1 is 3. Oops, pin 1 is 3. Pin 2 was 2. Pin 3 was 1. Pin 4. You're going the other way. Okay, so if we're looking at, let me just grab it. I'll show you.
Yeah, so you mean like 16, 14, 13, 12?
Where did I have it?
Oh, how's that label on?
Okay, so this is our multiplexer right here, and we're going to have ground is going to be 8, and it's going to be 7, and it's also going to be any of the pins that we assign to be, any of the inputs we assign to be 0. So I'm going to have X is going to be a switch, and it's going into S2. Y is a switch going into S1. Z is a switch going into S0. W is another switch that'll be going to various different places. Okay, what did we say was input 0 on the multiplexer? We said that one was 0, right? So now I am talking about our truth table, where we had 0, W, W bar, all those things. So when XYZ was 0, we said F was 1. When XYZ was 0, we said F was 1. So in our multiplexer, we're going to have VCC, which is going into 16. That is also going to be going into pin 4. That's high. That's high voltage. Okay? And then we said XYZ is 1 corresponds to W. So our pin that is W, so our switch that is W, that goes into input 1. And then XYZ is 2 is 0. So I'll have ground going into 2. And then, I'll get it right eventually, 3 is W. And so I3 is right here. I'm going to have switch W going into that. 4 is 0. So 4 is going to be ground. Five is W.
How's 4 ground and VCC?
4 is not VCC. 4. So I'm talking about I4, not pin 4.
Okay.
Pin 4 corresponds to input 0. So this is input 0, input 1, input 2, input 3. That is our value of XYZ, that 0, 1, 2, 3, 4. So pin 4 is VCC, but I4, which is pin 15, is ground. Did that answer your question?
I don't want to hold it up.
And no, it's important that everybody understand what's going on, because I don't think you're the only one who's confused on this, because everyone was given strange answers.
We have input 0 as 1.
Okay, so this is your chip. These are the pins on the chip. So these are the pins that are labeled on the chip. But these pins correspond to your multiplexer having values I0, I1, I2, I3, and so forth to I7. And that's what we were looking up earlier, and were labeling them. And I think we found that this was I0, I1, I2, I3. Does it not have a pin 0?
No, it doesn't.
It doesn't have a pin 0. I3, and then I4 was right here, and I5, and I6, and I7. So these 0, 1, 2, 3, 4, 5, 6, 7, those are the same as this XYZ in this chart right here.
So like, for example, the pin, let's say pin 6, I guess.
Pin 6.
Uh,
Pin 6 right here.
that would,
I believe that is Z0.
going back to the chart, how would we like, are we,
We don't, pin 6 is not, pin 6, if we look at our layout, pin 6 is, I think that was Z0, right?
yeah.
So that is, we're not going to be using that one.
Okay, so are we everything else though, are we deciphering that from that tube chart right there?
We are deciphering what goes into these inputs from this chart. So we're X, Y, and Z have to go into S0, S1, S2, and we're figuring out what goes into I0, I1, I2, I3, I4, I5, I6, I7 from our chart.
Okay, so that information of where the eyes are is like given, like where
That's the data sheet. That's,
Okay.
yes.
sorry.
So it's the same as what I have here. I mean, this is the chip that you're using.
Okay. I was just making sure.
Yeah.
And then the inputs, that's what we're getting from the chart.
That's what we're getting from the chart.
Okay.
So just to be clear, from our chart, we have X, Y, Z. We have them as binary numbers. We also have them as 0, 1, 2, 3, 4, 5, 6, 7. Those correspond to I0, I1, I2, I3, I4, I5, I6, I7. And those will correspond to pin numbers 4, 3, 2, 1, 15, 14, 13, 12, if I recall. And then we figured out on our chart that when XYZ was 0, our output, which I called F, which is going to be the same as Z, which is pin 5, is going to be that is what we're going to put into these inputs right here. And so I0 was 1, I1 was what? Anyone have it written down?
W.
W. I2 was 0, I3, W, I4, 0, W, 0, W0. And so into those pins, you're going to put 1, you're going to put VCC if it is 1, you'll put ground if it's 0, and you'll put W or not W if it's one of those.
You said you would put W if it's not 1 or 4. Sorry, I was right.
Okay, that's okay. So if this is our chip right here, then we're going to put 0 into pins 4, 2, 15, and 13. So wherever ground is, 15 and 13 and 4 and 2. We're also going to put ground into 7 and 8, was that right? Whatever our switches are for X, Y, and Z, we put X into whichever one is S2, Y into S1, and Z into S0.
I think 4 is
What?
I thought I0 is 1. How come I is 1?
I don't think I0 is 1. I0 is 4. Pin 1 is I3. Or do you mean the value that's going into it?
So f is 1 on xyz equals 0, right?
Yes. Oh,
So
I see. Yeah, I circled 4 when I should not have. Right. 4 should not be 4. Yes, that should not have been circled.
4 should be VCC.
4 should be VCC. So VCC would be just 4. Just 4 is VCC and 16. Yeah. And then W goes into pins 3, 1, and 14. So whatever switches W goes into pins 1, 3, and 14. And then you're also going to have a NOT gate. Very pretty. Okay, but of course this is not your exact function, so don't get hung up on what this one does, because I just made this one up.
So we'll have to get a separate NOT gate.
Yes, a separate chip NOT gate. And then, yes, so for the last one, you'd have to get a NOT gate and put that one in there. Okay, what time is it? 4:34. I've got to get to decoder, so I don't want to. Yes.
Trying to see the W, so W's connected, what does that stand for again?
The W was actually W. There's a switch, and so when we did our truth table, when we broke this up, and so we had to break it up because we only had 8 inputs, not 16. And so every 2 rows on our truth table have to correspond to 1 pin on our multiplexer. But we can't just say, okay, well, we're just going to make it that way. We still have to take into account this W. And so when I look at the 2 rows where XYZ are the same, and XYZ equals 1, I look at what my F value is, and I determine whether F is equal to 1, 0, or W. No, W is both 0 and 1. So like, look at when XYZ is 1.
Oh, okay, I see.
Now you see it?
Yeah.
Okay.
Okay.
Okay. Yeah. Just real quick before I do decoders. Let's say I have another function. Okay, so we're not going to do all 16 of these, but we're just going to do a few of them. Let's say that my function had min terms 1, 1, 8, no, let's see, 1, 4, 9, 11. 1, 4, 9, 11. That was my function. 1, 4, 9, 11. So I'm going to put f here, and I've got 1, 4, 9, and 11. Plus I've got the others on here that didn't fit. And let's say, again, I choose to use x, y, z. If I choose to use x, y, z, I'd break these up into every 2. And then my x, y, z values, just looking at just the x, y, z, that would be 0, 1, 2, 3, 4, 5. And then my output for 0, if I look, my f, I'll fill in zeros everywhere I don't have a 1. For x, y, z equal to 0, what's my output in terms of 0, 1, or w? W. When x, y, z is 1, what's my output? 0. When x, y, z is 2, what do I have? W naught. 3, 4, and 5. Oh, W. Just like when you're thinking you're getting it, and then I throw you. Okay, so y'all get that? Yeah, okay, all right. So I'm going to stop this, and then we're going to do decoders.